First of all, thank you to the organizers for inviting me here. I'm a bit tired. Um, yeah, so welcome to my talk. And I'll be talking about deep learning applications in industries and elsewhere. So all the use cases that I'm going to present, I have worked on them. So I've already been introduced, but yeah, I'd like to introduce myself again. So I'm working as a data scientist at Boost AI, which is a company based in Norway. And we are building chatbots. We are using deep learning and AI. And I used to take part in Kaggle a couple of years back. Now I don't have much time. And I'm always interested in automatic machine learning and large-scale classification of text data. And as it says, I like big data and I cannot lie, just like my t-shirt. So yeah, so a brief agenda for the talk that I'm going to do today. It's like I'm going to give some introduction about deep learning. I think you guys already know about deep learning, but everybody is doing that, so I must do that too. So next we have the implementation of deep neural networks, fine-tuning, and a few use cases, but no math. So it's going to be full like applied kind of talk. Yeah, I think I've tried to squeeze in a lot of information in my presentation. So if you're overwhelmed with it, and if I'm going too fast, don't stop me because we don't have time. Yeah, so what is deep learning? I mean, how many of you are data scientists here? How many of you train machine learning models? How many of you have deployed machine learning models in production? No. Yeah, so use deep learning, right? Cool. Yeah, so deep learning has become a buzzword. So like if you want to be a data scientist, you must add deep learning in your resume. I mean, then recruiters contact you and then they ask you if you have worked on scikit-learn. Yeah, so for me, deep learning is neural networks, not the shallow ones, but the deeper neural networks, more than 2-3 layers. And deep learning, it removes manual feature extraction steps. So like if you have images, deep learning in every single layer you're learning, your network is learning something new. And a lot of people think that it's a black box. I don't think that way, because deep learning does give you some kind of feature importance. As if you're talking about images, then you know what is being learned and which pixels are important. So we will talk about the history of deep neural networks, how these neural nets have, how the conv nets have evolved, and so we can see we have convolutional layers, subsampling layers, but yeah, and then we had max pooling introduced a few years back, and but we always need to go deeper. So Google came up with GoogleNet. It doesn't even fit properly on my screen. So yeah, lots of convolution layer inception models. But if I'm talking about all these neural nets in details, then yeah, you guys are going to be like a bored cat. So let's talk about what deep learning can do. Everybody knows these, I mean, identify butterfly, dog, cat. So these are the convolutional neural nets. Then we have the RCNNs, which identify different parts in image, so like different objects in an image. Yeah. Then we have a sleeping network. Okay, what happened here? Yeah. So the dogs don't like me. Yeah, so some dog and the muffins. If you're confused, then you will have dog for breakfast. Or pug. So yeah, but yeah, using deep learning, it's you can identify. So if you're wearing Google glasses and you're unable to distinguish between pug and a loaf of bread, then deep learning can help you. Then we have other things like natural language processing, NLP tasks, so for example, chatbots. And speech processing, you can use it for speech data. You have spectrogram of images, and you can like use a CNN or a time distributed layers. So deep learning is everywhere. It's a buzzword now. After big data, so there was this quote like big data is like teenage sex. So now deep learning is like teenage sex. Nobody knows how to do it, but they still claim that they know, and they have done it. So how do I implement deep nets? So I mean, if you don't know coding, it becomes pretty difficult for somebody who doesn't know coding to implement deep neural nets. But there are tools. So for example, you can implement them on your own right from scratch, all the back propagation, forward propagation. Then you will be a mess. Yeah, you can decompose the network into smaller parts and implement the layers separately. And then you have the training process. But you can also save yourself some time and fine tune based on what kind of task you have, mostly like for image tasks. So for fine tuning, we need to convert data in a proper format, which I'll discuss. And then you have the network definition and the solver. So this solver comes from Caffe. Have you guys used Caffe? Have you heard about Caffe? Cool. And then yeah, you have the training process again. So I'm going to discuss about Caffe and Keras. Caffe is no longer my favorite tool because Keras is more powerful. Yeah, but I did something using Caffe, so I'm going to discuss that. So for Caffe, why should you use Caffe? I mean, they claim that it's very, very fast. It's open source. It's modular, so you can divide it into different parts. And it's expression based, so you don't need to know about coding to implement a neural net using Caffe. And yeah, it has a huge community. So for Caffe, you need to convert your data first to a proper format. So like it has a database format called LMDB, either in that format or you can use images as raw. You have to define a network, which is a prototext file. And I will discuss about prototext. Then you have to define a solver and then train the net with or without pre-trained weights. So how do you define a solver? So like here, the network name is train_val.prototext, which is a training prototext file. Then you have the number of test iterations, the interval, whether you want, what kind of verbosity you want, and learning rate policies and stuff. It's been a long time since I heard that ringtone. Yeah, then you have a snapshot prefixes like where you're saving the model weights, the folder location. And solver mode, you can switch between CPU and GPU. So it's pretty simple. And I mean, you can find these prototexts everywhere on the internet. You can just copy paste. And then you define the network. So it was train_val.prototext. So you have a network name. So this is Lenet. And you have the input dimensions like we always do for convnets. And you define layers as separate modules. So you have convolutional layer, pooling layer. So here it's max pooling. And yeah, the rest of the part. So it's using softmax and giving you the probability values. So training a net using Caffe is a very difficult task. I mean, you have to install Caffe, and then you have to use this command. So it becomes pretty difficult. Yeah, so you just do like Caffe train, and then you specify your solver text file. Fine tuning. So why you should fine tune? So I mean, if you're training a neural network from scratch, maybe you won't get very good results. So what you can go for is fine tuning. So Yeah, why I'm talking about GoogleNet. I was fine-tuning using GoogleNet for a given problem, and yeah, why GoogleNet? It had Google, so I wanted to try. So it won the ILS VRC challenge 2014, and it was complicated, and I wanted to change some parameters and see how it performs for my task. So there is a cafe model zoo, and you can find all kinds of pre-trained models there, including GoogleNet. So the first use case that I'm going to talk about is distinguishing between honeybees and bumblebees. I mean, can you guys distinguish between honeybees and bumblebees? Oh, nice. You should teach me. I'm scared of bees. They don't like me. But it's tougher than distinguishing between a dog and a cat. So this was actually a challenge by Metis, and you can find it on drivendata.org. It had like 80% positive samples and 20% negative. Don't ask me which ones were positive or negative. I'm not sure. One of them. So, and the evaluation metric was area under the ROC curve. So I started with a very basic, simple network. I implemented it from scratch. And so you like 3 convolutional layers and max pooling. And the output is 2 because there are 2 classes, honeybees and bumblebees. And it went something like this. So this is the loss here, and you can see like loss is between 0.4344, which is too high. So I was not getting very good accuracy. AUC was also like somewhere around 0.85, which was too low. So what I did was started with GoogleNet and started fine-tuning it. So you have to create, first to fine-tune using Caffe, you have to create the training and test files. So then you can grab the prototext files from the model zoo that I already told in the previous slides. And you need to modify them to fit according to your data. And then run the Caffe solver. So this is what like this file looks like. You have the file path and the label, so which you give in the Caffe while training it. And so to create this, I'm using Python for everything. So to do that, to create these kind of files, it's pretty easy. You just specify train and test and keep your images in separate folders. And you can find the code on my GitHub. And then the next thing is you need to make some changes in the prototext file. So you can see like a diff here, what I've changed. So I've changed from data to image data. Data was the LMDB format that Caffe was using. And so I changed the batch size and height and width. Next changes in train val were like, again, the batch size. And you need to change the last layer, name of the last layer for fine tuning. And I also changed the dropout ratio. Yeah, number of output was 1000 for GoogleNet. Now we need just 2. Yeah, and some more changes. I mean, and these were the changes in solver. I think you have already seen this before. So yeah, to fine tune, it's just a simple command line. And I wanted to see if the network is learning something new. So I initialized the model with random weights. So this is just some random stuff. So you can see like honeybees and bumblebees they are mixed right now. Then I used the pre-trained weights from GoogleNet. So you can see, I mean, they are forming the blue. I don't know which one is which, honeybee or bumblebee, but yeah, one of them is forming a small cluster. But what happens after fine-tuning? You get a very good separation between these 2 classes. So breaking down the inception layers. So for every feature layer, here I'm representing the accuracy. logistic regression accuracy. So I just extract the weights and I put a logistic regression on top of it and see what's happening. So you can see like the accuracy is going over 90% for last layer, fine-tuned. So why we should fine-tune? I mean, it is, of course, it's very, very fast. It is, most of the times it's better, I cannot say always. And there's no need to reinvent the wheel. So yeah, that's fine-tuning. And the same thing can be done in Python. So for Python, I'm just using Keras all the time. Do you guys work with Keras? Cool. So Cafe also has a Python interface. And there is TensorFlow, Theano, Lasagna, Keras, Neon from Nirvana Systems. There are a few more. So you can use any of them. I mean, Keras, for me, it's the easiest, very simple. So the next use case that I'm going to discuss is about classification of search queries. So this is something that I did in one of my jobs. So last 3 years, this is my 6th job. So yeah, nothing to be proud of. Yeah, so this thing, I mean, for a data scientist, if your model is not going into production, you should switch the company. Yeah, but this went into production. So why should we classify search queries? So search queries are something like if you're searching for iPhone 8, iPhone X, or yeah, whatever this new one. So for businesses, they want to find out the user intention. So what is the user thinking when they're looking for something, or like they're searching for things to do in Munich or something like that? So what's in your mind? Because if you have a website which sells electronics items and you don't want visitors which are interested in furniture, right? And yeah, you can track the keywords according to the buying cycle. So buying cycle is like user making himself aware of the product, or user is considering to buy a product, but without any user logs. Yeah, so, and of course, it's for optimization of the website content. For data scientists, yeah, hundreds of millions of unlabeled keywords. Big challenge. So word2vec in search queries is something like normal word2vec. So you have a vector for Germany, France, Berlin, and Paris, and you subtract Germany from Berlin and add France to it, you get a vector which is very close to Paris. And in search queries, it's become something like this. So if you're asking what's the weather going to be in Berlin, so you get the weather forecast for Berlin. You don't get other stupid stuff, right? So it's just sentence to vector instead of word to vector in this case. So for this, I used LSTMs. So if you are searching for the White House, so every word can be represented as a vector. This creates a sequence for LSTM, which it goes into the LSTM model. I mean, this is the sequence, and yeah, it can be implemented in like 10 lines of code using Keras. So you have the LSTM layer. I added 2 LSTM layers, dropout, and in the end, a sigmoid activation. So yeah, you get United States, president, politician, these results. But these LSTMs are very, very slow if you have 100 million samples. So I ended up using something else. Yeah, this was the performance of the network. I didn't have patience to wait for the error to decrease, and it was taking a hell lot of time for every single epoch. Yeah, so queries can be divided into, so that was like classifying into 10,000s of categories, but search queries can also be divided into navigational, transactional, or informational queries. So navigational is something like if you're searching for Datageeks data day, you get the rocks website. And transactional are like searching for iPhone, or informational, things to do in Munich. I won't go into details of these 4 classes. So what I did was I represented every search query using an image, which is created from word-to-vec vectors. So when you search for something on Google, you get 10 search results. I created word-to-vec representations for each and every title that you get in the result, and then you can feed it into a convolutional neural net. So now, of course, you cannot distinguish between Irish or apple juice, but the convolutional nets can. So Guild Wars, it's a game, and apple juice. So I don't see much difference. So for me, it's like a loaf of bread again. So then I went into these machine learning models. I started with some boosted trees, word-to-vec embeddings to like classify them into different categories. And in the end, I ended up using TF-IDF and XGBoost. So how do you feed these features in convnets? Either use the images directly, or you can use the random crops. So a very simple method to combine these random crops is like taking an average. And then you have these neural nets. I mean, it's a simple sequential model using dense layers in Keras. And the same can be done for convolutional models. So I don't think this code is on my GitHub, but anyways. Next, before proceeding to other use cases, I'll talk about approaching any machine learning problem. So 2 years back when I was working in a university, doing my PhD, which I quit. So I came up with this framework. So it's pretty simple, man. Come on. So you have the data set, you split the data set, then you have validation set, training set, and test set separately, and then you decide what kind of data you have, numerical, categorical, or text data. If you have categorical, you convert it to labels or binarize, you can do one-hot encoding, then you stack different models. You can do some kind of decompositions like PCA or LDA. And you can also check out the paper for more detailed version of this. And yeah, in the end, you're evaluating every combination, and you select the best model that you have. So this framework I'd never released publicly, so don't ask me to release it. But yeah, if you want to help me with implementing this from scratch again, yeah, then you're welcome. So based on the same thing, I did something like optimization of neural nets, and it's again pretty simple. So it's very similar, and this was also a part of ICML workshop. But selecting the neural net architecture, it's not something trivial. So what I do